So you guys know the Minuteman machine, arguably the fastest FDM printer in existence. And probably you want to see me pushing for that sub 60-second run here, but we're gonna do something else today because this is Minuteman's older brother. And I think it's finally time to revive the beast. So if you have no idea what this machine is all about, there is a 7-part series where I did all the conversion.
Damn boy, that went perfect.
Somewhere in the meantime, I did a video about production printing on a belt that was integrated in here, and since then it is pretty much sitting. And as you can see, it did collect a lot of dust. So, but the first step will be to get in the old switching cabinet, clipperize this whole thing, make it 2026, and equip this with one of my latest open source hot ends, and see if we can finally get rid of the cooling bottleneck we have on all these smaller machines like the MK3 or the CR10 back there. So with the hope being that with this massive footprint, we can finally run one of those hot ends to its maximum. So my name is Jan, and I build stuff so you don't have to. Enjoy the episode.
Da 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 da.
So let's do a very quick tour on the machine so we know what we're dealing with here. So this is pretty much the same base as the Minuteman machine. This is a Johansson Cordimet 701. I have no real idea from when this machine is built, but I do have some original hardware here. And this is pretty hilarious if you ask me. So this machine is from the same range, and as you can see our travel is 700 by 450 by 350. We can extend the X a bit. I think on this, because of the retrofit I did, it was 750 millimeters. And at the time, this was around this price in Deutsche Mark. Before tax, by the way. So what is original from the machine is of course the whole base and the complete air bearing system. So X-axis, for example, does run on 2 pads, 3 pads, 5 pads, and another 2 in the back, so 7 pads in total. Y-axis, however, is consisting by 4 bigger pads which totally wrap around this granite beam up here. And there is actually an episode where I did crash this air bearing and I did the complete relapping of this. And then my retrofit here has been like there is this servo, and this up there. And all of these have been fitted with ball screws. Pretty cheap ball screws, admittedly. And then pretty much in one of the last videos I printed this cover here, which showed me a lot of the pros and cons of my concept here. And then this is the switching cabinet. This has gone through a lot of iterations. Right now it is of course being controlled by an RAMS 1.4. There has been a complete back-off PLC in here with sophisticated servo drives and all that stuff, but in one sentence, never back off again. Anyway, let me try to connect to this RAMs and see if we can get any movement in here. And right after that, we're gonna install some brand new hardware, which is equipped with all the latest features. Oh, this is actually pretty sick. Do you remember the good old times? Fronter face. So I'm just moving mid-air, obviously. Few of those hoses have gave up, so it's pretty loud. Gotta replace these. The X-axis ball screw was also very crunchy from the beginning. So it doesn't sound, it is very loud. So I got two main construction sites right now. The first is this Hotend /extruder setup. This is the thing that has been on here, self-designed Hotend from 2018. When I say self-designed, this is a complete one-off. Every single part here is built by myself because this is essentially the one I had to build 20 times with very close tolerances to make this here work. And I already went ahead and made some prototyping parts to accommodate the Bondtech one-off 4-way extruder. And then everything below there is going to be powered by my open source design. So essentially this machine will be a really good opportunity to test things because everything is really open. You can grab stuff, you can have a pretty good look at things, it's precise. I do have a sophisticated switching cabinet that is open and I don't have to like fiddle around in some really tight space, etc. So we're going to test a lot of things and mainly we're going to put on our next iteration of my open source Hotend. This is the version 0.92, so we're still in beta phase, but we're getting increasingly closer. And for a brief look on the nomenclature I choose. So this is obviously the R stands for Rötz, my name. This is the 4-way inlet version. And this is the pi because it's basically each of the 4 segments is a quarter of a complete circle. While this on the other hand is the core. And basically the 2 most outer channels do a complete wrap over the 2 inner channels. And I want to test things like having the core of the extruded filament as a conductive one and then the wrapped around part as an electrical insulator. We're going to see if we can like print coils with it in one go or something like that. Each of these will be interchangeable on here. Yep. Would be a great time to go down in the comments and tell me what I should test first. So I'm going to be preparing all of these parts, cutting threads, etc. Then I got all the other things here. Beautiful looking prints on the Core 1L. These are printed in Prusa's PC Blend Carbon Fiber Black. And we're gonna see if they hold up. And the other thing I'm working on is clipperizing it. Originally I wanted to go with a different kind of mainboard back then. But as it turns out, the servos I'm using do require like 5-volt input signals to step in direction. And all of these more modern mainboards tend to use 3.3 volts, while this one, and I measured this yesterday, is putting around 4.7 volts on these channels. And I'm gonna install this, measure what the voltage here is, and if I think this will be safe for the future. And if not, we're going to go with some optocouplers and raise the voltage of those outputs. Alright, so this is the complete assembly. Cold end mounted solidly to this adapter to the Z-axis. Then I've made my mind up. I'm going to go with the pi version. See what maximum flow is out there and then do some maybe colored prints. And basically this goes together like this. This sits in here. And then we're gonna make use of these dovetail features. Usually they were designed to attach whatever you want to do, like probes and cooling fans and shrouds and whatnot. But since this Bondtech one-off doesn't have like mating features to whatever I designed here, I made this adapter as well that connects with the dovetails here. And I inserted some N3 nuts here, so as soon as I go with the slightest bit of tension on the screw, they lock this in place really, really solidly. A weekend has passed and I got this to run on this optocoupler setup. Basically converting the 3.3 volt, the Octopus board is giving out and amplifying it up to 24 volts and then feeding this into the servo. And this does run, but I made some tests where like the cutoff frequency is kind of about, and we could make it work, but yeah, it's kind of right on the edge of where our travel moves are, and I don't want to be like losing steps. This is losing steps the hard way because the server will do PID. Yeah, it's gonna mess up a lot of things if step counts are actually lost in this kind of setup. So my plan is to conduct the first tests with this kind of existing setup. I left it intentionally to check this out here, and then do some proper things. So either I'm gonna build something more sophisticated out of a line driver, either RS422 or RS485, or we're gonna do a complete switch over to probably a do-it board, which can do 5 volts natively. But as always, I'm also open for suggestions down in the comment section on how to manage this safely. As stated before, my main thing is to find out if it is actually possible to print the whole surface without a heated bed. Let's do that with this solution before I got way too invested in this here. Yada yada. Yeah, this is where we're at right now. As you can see, filament is on there. Everything's put together. Of course, we got a makeshift wiring here. It's always time to clean this up afterwards. I mean, I keep telling me, but you know the deal. Let's see where filament comes out. All right, I'm calling this a success. No filament to be seen here, but of course we don't have high pressures in the melt zone. So let us talk printing surfaces for a second. So the whole reason why this doesn't have a heated bed right now isn't because I'm cheaping out here or something. It is because this machine is geometrically almost perfect. So everything, the flatness of the table, the perpendicularity of all the axes has been in sub-micron level accuracy when this machine was brand new from factory. Of course, I have messed around with it. The perpendicularity between the table and the x-axis has never been touched by me, but I have been a whole lot on this here. So this could be tilted in various ways. And at some point I would like to get into this, break out the micron indicator and try to get this back to 0, but we're not there yet. The fact of the matter is, as soon as I put a heated bed on top of here, I do lose all of that accuracy. So right now I need a single point probe somewhere on the table, and then I know my first layer will always be flat as fuck. And now, the biggest question I get asked on the Minuteman machine is how do you get bed adhesion? And I've stated this multiple times, but we're gonna do this again. What I use here is pretty simple and most likely a 2018 setup, but it does work for me pretty good, and especially with various kind of materials. I've successfully printed PLA, PETG, ASA, ABS, and various other blends on here. And the whole thing is a sheet of build tech. This is the one I have cut out of here. This is the build tech PEI sheet. And then on top of that, I use some ABS dissolved in acetone. So this is just ABS filament cut down to small particles and then dissolved in acetone. And this is spread evenly on the printing surface, which gives it a very nice texture where all the materials bond pretty well to. But then again, it's removable and I haven't like reapplied this for, let's say, 50 prints or something. And you can clean this with isopropyl alcohol or brake cleaner or something like that. It will just clean it. And as soon as you touch it with acetone, you can get it completely wiped off. I have no idea what it does to the PEI, but I'm not interested in the PEI. I'm interested in the combination of the two things. And yeah, on this machine, I want to try if I can use this information to go big format and actually get rather big molds or something sticking to a cold bed. We're gonna use the remaining thing I got here as a reference group, glue this on the machine, apply the acetone on top. And then I do have some knockoff material, which will do as a test group. In the ad, the whole ridiculous stuff on top of here wasn't there, so we're gonna have to live with that. And see if it's actually the build tag or just any other PEI sheet will do, and the acetone jizz is actually the important thing here. And if it works with these guys, I'm gonna cover the whole bed with it, and then we'll see if we can print big things with it. So this has the right consistency. Thick, gooey mix here. And the way I've applied this before is by using a folded paper towel, just dipping it in, and then you have just a few seconds to actually apply this. I'm gonna have to see how that works for larger surfaces, so let me find out first. So I've prepared 3 printing surfaces, straight on the granite, with the build tag, original PEI sheet, with a knockoff material. I applied this here thinner than here, unintentionally. We'll see. This is a 0.8mm nozzle, and I think we extrude in 2mm wide lines. So we already got our first results. So as you can see here, this is lifting from the plate, but it is not from the glue. It is the glue to the granite that is lifting. So this is a strong indication for let's use something that is actually building a better interface layer. I'm gonna let this run until we get in the spiral mode here. So this rectangle is actually pretty much the worst when it comes to layer adhesion, because these thick walls will tend to pull these edges up. There's no brim or whatsoever in the corners. So just thick layers pulling these corners up. We'll repeat that on the other 2 surfaces. And yeah, now it's going downhill really fast. Oh, this X-axis nut does not like that. As I said, I don't really care about that motion hardware. If this goes bad, it goes bad. And then we'll replace it with something proper. This is the same with the servos. As I said, these were budget material back then. If I want to upgrade these, I will do something sophisticated with a proper bus system to connect to. So, if you're a company, you're selling motion hardware and you want to see that on the machine, just write me an email, okay? You can dream, right? So while this is doing the first layer, the last one did peel off with all the glue attached. So here, this is a no-go. This is like granite again. We'll see if it's better here. So it's not too easy to show, but this whole machine is basically shaken like crazy on when it does direction changes. So that is because this machine is sitting on these 4 pads, which do have big springs in it. Whole machine is 1.3 tons, and I have to look it up. I calculated this once. I think this upper part is basically all X, Y, Z axis is at least 200 kilograms that it is weighing around. So therefore there is a lot of inertia going on, but the machine itself is pretty stiff in it because of all the air bearings in the Z axis, and even though this is a very long shaft down here, there is pretty much no ringing to be seen, even with high corner speeds. So this is pretty interesting. I will be very excited for the day when this thing runs Clipper and we're gonna do some input shaper measurements here on this machine. I have no idea where this frequency is actually lying, but I guess it's pretty damn low. There are 18 air bearings on that machine total. They consume quite a lot of air, obviously, and you need clean air. I don't know if mine is clean enough, but since I'm the guy that has to repair all of that, if it crashes, I'm okay with whatever I got here. If you're interested how I do hit these 3 areas, I got a texture of the machine base here imported in Prusa Slicer, and these do have all these location marks and threads built into it. I do have to play with that offset a bit. I think it's like 10 millimeters too far to the left, but I'll get that sorted. There is, if this machine will be used more in the future, I do have to start with a profile from scratch. This is just arbitrary values. Nothing here is tuned. So there is a bit of lifting. As you can see here in this corner, basically all the corners. But again, worst case scenario, let's see if this one finishes. I had to pull quite hard to get this off. So, and again, it's not the glue that has failed to the print, it is the glue not sticking to the layer here, especially on the outside, so it has taken the glue with it. Alright, so let's see then if this will work. Okay, so far it does look pretty good. I think this corner just has started lifting. Okay, it is starting to give up. I'm gonna stop this print and we'll see what loosens first. This is brutal adhesion. So the majority of this glue has been sticking here. This surface gets a bit dull after the first print, but this will stick pretty well to it for the next print. I mean, this has of course lifted, but my guess is if I would put this on pretty much any printer, there would also be warpage. Maybe I'm gonna test this. So I think with proper settings, maybe a few degrees more on temp and some Mickey Mouse ears here, this would probably be in an okayish state to print. I don't know. Let me think about that for a night. So here's what we're gonna do. This one worked the best out of the three. If I put all of these 5 here on the build plate, we can have quite a large area to work with. I think we can at least do some proper flow testing and such. The areas where I had like the most deposition of ABS material were the most likely ones to actually peel off. So we're gonna go with a very light coating on the next one. And as we have found out, the glue itself is sticking to the PLA in this case really good. But the bottleneck seems to be it lifting off from our surface below. What I didn't do initially is wiping those guys off completely before I applied the ABS jizz. So we're gonna reset them all the way, make them fat, fingerprint free, etc. And then see how good of a sticking effect we can reach here on this cold bed. And when I say cold bed, it is still pretty cold in here. And before this granite really warms up, it's gonna be late in the summer, I guess. So this is somewhere in the 10 to 13 degree range. And I think it's somewhat promising that we can at least have something like this applied on here with loads and loads of flow and thick walls. Speaking of thick walls, the Core 1L did finish a duct on here, again printed in PC Blend carbon fiber. So I'm gonna put again the leaf blower on here to have at least some kind of cooling. And then let's see what this hot end can do and maybe switch over to the next one. I have no idea. Let's just roll with it. There we are. So this should give us 440 by 430. And if this works, I'll buy a few more of these and extend it all the way to the 750 millimeters of X travel. So this is how the tool head looks like. This is the standard hole in the Z-axis from the CMM to accept tooling. I adapted that CPAP fan, routed all the way up there, and this is my easy switch for plugging in cooling. This So we've made it rather far, but now it's starting to lift here. We're at 50 cubic millimeters a second. I mean, you hear those cracks? This is basically where it's peeling off. I mean, it's also like a reference for hard to stick materials. The brim is not too big and I adjusted things here in the first layer. So this shows some interesting properties. We're not talking VFAs here. The things that in here, I think, are due to this extruder. Some of these gears do have ground at some point and there's material sitting in there, and therefore you do have a changing rolling diameter. On top of, this is the first prototype Bondtech has ever built. the spacers between all those lanes are not perfect. I relapped one of those, but if the spacing isn't 100% correct, the filament may not be grabbed by the center of the cutout. This also changes the circumference again by just one of these. So therefore, I guess the reason for not 100% consistent extrusion is going to be somewhere in here. Regarding the printing surface. So of course, heated beds are there for a reason. And the smart person that would want to have a working and reliable 3D printer would go ahead and build a heated print bed. And it's not that I haven't. See, this is the first heated print bed this printer has had years ago. And also, you see how dusty that container is, but this is what I bought years ago to heat all of this. So I'm not unprepared, but I'm also never building printers that do stuff any other printers can do. So I'm specifically searching for an application which no other can. And as you can see, I've stuck a dial indicator on here. And so there is something like 10 microns on all the way of Y travel. This would be an episode in itself. This has something to do with this scale here. See, let me see if I can get both in one shot. If I move this back here, you can see there's tiny movement of the needle on this dial indicator. So what this apparatus does is basically cancelling out the weight of the tool head being here in front and shifting the whole y-axis a bit down. This has to be calibrated on point, and of course I'm adding weight that hasn't been there before, and I've done all sorts of things to this machine. As well as hijacking the pneumatic system for all the air bearings. So this has to be calibrated. But I guess then we could stick a micron dial indicator on here and get this very close to zero on the whole travel. So to show that this isn't like in mid-air, this repeats to zero, let's do the X movement. So the question is, can you think of an application where having a print bed that is 700 by 430 millimeters wide, flat, pretty much to a few microns, because of course I'm adding these kind of sheets up. I measured those have a few hundredth of a millimeter deviation in itself, but we could get sophisticated PEI or Ultim sheets on there that are like ground or something. So it would be possible to get a very flat surface, and usual 3D printers do produce very good first layers that have a very fine adjusted tip to print bed distance, but they can be all sorts of warpage inside, so basically in the neighborhood of 1/10 of millimeters. So let me know down in the comments if you see any application that only would be possible on a machine like this. Okay, I don't want to chase flow tests. This one was, as I said, somewhere to 60 cubic millimeters has this been. Because we've already shown in previous episodes that this Hotend is capable of 200 cubic millimeters a second on this setup. And if you choose, like I did here on the Prusa MK3 with 2 LGXs, I was able to run 200 as well on a 2 filament setup. So if you scale this up, I'm pretty sure we could hit 300 cubic millimeters with the right filament, but I want to do something else, which is a bit more scientific. Let's run the R4-core. So in theory, I should be able to pull the lower part out, stick this in, and then just run this. And if everything goes to plan and I've done my homework, we should have an embedded core into an outer shell. So I've ran quite some material through here. The setup looks like this. We got on both sides a blue Fibology high-speed PLA coming in the outside lane and then a black one in the inside, same as here. So let's hop over to my screen. I want to show you how this is designed, and then I'm going to show you some of the results I got from the extrusion. So this is what's installed on the machine. As you can see here, R4-core. And its intended purpose is to create an inner core as well as a surrounding shell. If I've done my design right, you shouldn't be able to see the core from the outside. That would be interesting for a number of reasons, for creating your own filaments, for creating things like a conductive core with an insulating shell, you name it. So it's rather hard to have a look inside here because there is so much going on. But essentially, let's say we have melt channel 1, 2, 3 and 4. Channels 2 and 3 are just standard round channels that will intersect somewhere like here and combine their flow to a single diameter of roughly 1.5 millimeters. So we're combining two channels to a round outlet. And in our particular case, this is the black filament. So now, channels 1 and 4 do look something like this. We're trying to get this flowing here and wrapped around the circular outlet we've spoken before from channels 2 and 3. Right here we can have a look on how this is approaching each other. So 2 and 3 combining. Now the 1 and 4 channel is slowly diverging to a different channel geometry, and then here they're being put on top of each other. So now that I see this and had the very first results in my hand, I would immediately know a few things I would have done better. But I made this design a few months ago actually, and it was sitting here so I could do my very first test, and I will keep on developing this. You can put down in the comments if you want to have this step file as is for your own testings if you want to, or do you want me to wait until I have this fully figured out and then release the files here? But yeah, this is then all being combined into a single circular section of 2 millimeters and then being fed into our standard nozzle. So this is what I got as a result. It is really hard to see and to film, and as you can see, the wraparound isn't perfect. I would say it is somewhere in the 80% range. I did some tests with varying temperatures, so starting from 180 to somewhere in the neighborhood of 250 degrees, but the wraparound situation didn't change. And this does make sense because it is the same material on both lanes, and therefore we're changing all the parameters at once. So the very obvious changes I have to make are in this combining section. It is crystal clear that the part where black is showing is coming right up here, and I should have made this way easier to flow into the most outer sections. But we're using very hands-on approaches here without any simulation on this part. And now it is really easy to change a few things here and there based off our experience, and then yeah, we're off to the races again. So what we can do now in terms of figuring this out is to use different set of material. Let's put in some different PLA material, which is on the very viscous side of things, and see if we can get a complete wraparound. So what I'm trying here, gonna go with a very slow upwards command and then extruding material and blowing some air on it to essentially create a very big extrusion that we hopefully can get a slice out and see what the inside is made of. That is definitely one of the weirdest things that I've ever 3D printed. And if we're just talking about single point bed adhesion, so I think this is really impressive. So I'd like to add, this is not just the weirdest thing I've printed, this is also one of the coolest. So as you can see, this is the specimen, and right here in the section where it was pretty consistent, I sliced it open, gave it a quick lap. As in material science, you can see what the cross section looks like. So this here is in the neighborhood of 7 millimeters. So of course there are so many things involved, like temperature, back pressure, and extrusion speed especially. So we're going way slower here as I did before when just extruding free air. Also you can see my mixing ratio is 50-50 right now, 2 filaments from each. I have discussed with myself a lot if I should go 1 filament inlet for the core and 2 for the outside, but it wasn't really matching up with the design here. I'm planning to do a 3x filament hot end, but I'm not quite there yet. So yeah, I went back, made some tests with varying speeds, and as you can see, the latest ones are of complete blue color. There is no such thing as a black line anymore. For printing attempts, it would be nice to have that throughout all the ranges of printing speeds. So for me, one of the hardest things in these endeavors is actually doing this research work and filming this at the same time, because it's pretty much like chasing a rabbit and you never know which turn it's gonna take next. So I don't know, this is going to be a messy video, I guess, but I take you on a tour. Next up, we're trying to do something that is on my list for quite some time. I got the feeling that I won't be getting the results I want, but hear me out. So I got this here. I have no affiliation with those guys, and neither do I have lots of experience with conductive filaments, at least not with the thermoplastic ones. So I got some samples on there and also fed in the hot end. And what I'm trying to do is print a spiral with, of course, having the conductive material as a core and the isolating PLA as a shell, to see if the future will hold 3D printed coils of some sort. I know the resistance of this coil will be terrible, even if it would be as advertised. This claims to have like somewhere in the range of 100 kilo ohms over a distance of 10 centimeters. It doesn't give any information on the cross section it is measured by, but I couldn't reproduce any of these coming straight from the spool. Let's see if it differs once we have put it through the hot end. So let me try to come up with some feeds and speeds for a, let's say, 50 millimeter spiral. We're gonna go big cross sections. I try to do like 4 millimeters or something of line width, and we're gonna go very, very slowly. Let's see if I can do that. From all of these parameters, the speed was doing the most. So I'm gonna go down with speed again. I could imagine that also temperature is now too high. We're at 200 degrees. I could imagine we had to go down to like 180 or something. But I've seen so many first tests of something completely new. If you ask me, this is something you totally find parameters for it to work. It's starting to close up here. So for extrusion, especially with those longer melt channels, etc., dialing something in, you have to at least give it a few minutes to fully settle in and draw any conclusions from it. It seems like every new rotation it does brings us a different result here. So I fooled around with loads and loads of parameters. So first of all, I hacked the E-steps per command line, and now instead of 1 millimeter, which was kind of the upper limit Orca slicer would let me do, we're extruding at roughly 2 millimeters of layer height. Then there's some added flow, 25% on. Temperature is at 195, and speed, I don't know, 7% of 60, but I'll let this print for a while, maybe fool around with another parameters, and then we'll do a cross section again and see what the separation looks like. So I'm calling this a huge W. So these are definitely 100% separated from each other. Down here you can see where we're coming from. Random parameters. I mean, even there it is working, so you can see with the right set of parameters you can even have very low layer heights working. As up here we're somewhere like 175 in height and 3 millimeters in width. So this is our ratio there. So I have melted 2 needles into the inner part. And this is showing conductivity. This is not. Okay, I gotta go for today. Let's wrap this up tomorrow. Let's talk about a few things, starting with the Hotend itself. So first off, my latest adaptation here, I'm really happy with how this turned out. Not just that it's looking pretty dope on here, and everything pretty much worked out of the gate, this is the main thing. If you've seen previous videos about this Hotend, you have seen problems with leaking heat breaks and all sorts of other stuff, so this seems to be pretty much solved. And the way that everything here starts to come together, so basically never remove these heat breaks. It takes a few minutes to change these out. I didn't even have to adjust the Z height, it just worked out of the gate. And you can now pretty much take everything from the ecosystem. So if you have a look here, basically you could also take the 2X version. I mean, obviously you can't plug this in here, but you could take the 2X version and put it on the 4X cold end. So basically everything has been done in the same ecosystem. And in terms of extruders, I know you guys don't have the 4X Bondtech version I do have, but you can pretty much choose every extruder you want and run it in a direct or Bowden drive configuration. And I would be really happy to see all of your approaches, how you solve that, and if it's a good one, maybe we can publish it as well. The best way to do that is to come on over to my Discord channel, share your results there. Let's have an open discussion about it and yeah, see where we can improve or publish it right away. Also, I want to take the time to thank all my Patreons. This is enabling me to do all this crazy stuff here, basically in my free time. So thank you, all you people. If you want to have this Hotend, there are some options, but the first step is always to get on over to my GitHub page. It will be somewhere down in the video box. And there is all sorts of files. I uploaded them as STL and step files. If you want to do something by yourself, take this as a base. And all the parts are from the catalog and can be found in the bill of materials. Standard heat breaks from the Chimera ecosystem, standard 30x30 fan, standard 24 volts 6mm cartridge heaters, M6 rep style nozzles, you name it. The two obvious parts are SLM printed in aluminum, and you can either grab those files and go to any SLM manufacturer you desire, or you can do that with our today's video sponsor, which is PCBWay. In terms of acquiring the Hotend over PCBWay, there are two options available. The first, and obviously cheaper one, is to have them right out of the machine. It isn't guaranteed that these heaters do fit in here and the threads are just printed in there. You have to chase them with a tab. The second version, and this is what you can do by downloading also the technical drawing from my GitHub and uploading that while you're in the process on the PCBWay website. Then you can have this with all the threads being done, and all other miscellaneous hardware will fit right out of the gate. So PCBWay is really a long-term sponsor of this project, and we have been working together very successfully. I've shown the quality of those parts in a number of videos now, and acquiring parts is really easy. You just hop on over to the PCBWay website, choose your desired process. They offer all sorts of 3D printing applications, sheet metal design, PCB design, milling, turning in up to 5 axes. Basically, you name it. You upload your file, choose your desired material as well as quantity, and you get an instant quote. So, if you go down in the video description, the top link will give you a small discount on your first order there. So again, thank you PCBWay for sponsoring this episode. Let's go back to the machine. And yeah, with this particular R4-Core Hotend, I'm really happy with the results. I mean, I couldn't get any conductivity measurement here. I saw a PDF file from another manufacturer of conductive filaments that points out that the printing temperature makes a huge difference in conductivity. So I was running this at 190 to get consistent layer buildup. So maybe I would have had to extrude this at 250 to get some kind of conductivity. Who knows? But the whole point is that it's not the time to straight dive into another rabbit hole chasing conductivity. This is just one of my examples of how this technology could be used. There are a lot of other options. Let me tell you about 2 of those which I have in mind, and then you can give me your ideas in the comments and we'll see which of those rabbit holes we're gonna eventually discover in the next episodes. So what we would be able to do is use this as a base. Take the most outer lanes and form actually the shell of whatever we want to print. The inside can look completely different than it does here. And probably it isn't even filament based. So what we could do is run a single channel, which, for example, has some iron powder in it or any other whatsoever. And then basically just gravity feed stuff in the middle, hopefully still having laminar flow, and embedding whatever we put in here in this middle channel then into a print. So this would probably lead to some really good conductivity, as well as heavy parts, as well as, I don't know, parameters of the finished print. We'll see. Second one I have in mind for quite some time is to actually get rid of these channels per se, have some kind of a plug in here, put a very controllable amount of shop air on here to basically recreate blow molding. So blow molding is a process, let's say in the same neighborhood as injection molding, but what they'll do is they're going to extrude a hollow sleeve. Then some sort of mold is going to close around this, and then when they apply some sort of pressure, lay tightly against the mold halves. And then they obviously demold it and you have your finished part. So basically all sorts of shampoo bottles or whatsoever are made in this process. I know it will be a challenge, but what we could try to do is to recreate this, and instead of extruding a solid filament, we could extrude a hollow tubing, which of course has very interesting properties, such as being very light. You could also have like channels that you could do electroplate later on, or just gonna contain any sort of fluid. So I think this would be a really interesting one. And I'm really hyped to hear all about your ideas. What should we do in the next episodes, basically? Moving on, the machine itself. So first off, I'm really happy that this thing is moving again. It has collected way more dust than I wanted to have it. And I finally pulled the trigger to do some work on it again. Obviously, there are a lot of construction sites I have to dig up now. I think it's pretty hilarious that a RAMS 1.4 is controlling this machine still. And just for the sake of this thing not being able to do proper voltage control. So what I want to do in terms of getting Clipper or Calico on this system is to have a proper connection between a mainboard and servo drives. So again, I'm interested in how you would solve this. As I said, there's going to be line drivers, which we could use. The optocoupler thing I kind of threw in the trash because I have no idea how fast or high resolution wise I'm going to be feeding information to these servers in the future. I want to have something sophisticated where there's not a bottleneck in minute one. And yeah, one of the biggest concerns running this machine is safety. Under normal circumstances, I would never run a machine like this. Let me explain. Because everything here was planned differently, and then at the end of the day, switched back again to RAMS 1.4 a few years ago, because I couldn't get it going otherwise. Everything here is also just hacked together for the sake of running it on a 3D printing mainboard. And yeah, I mean, if your printer, I don't know, loses steps, loses origin, a belt rips apart or whatsoever, it's not a big deal. It's gonna bump into probably some 3D printed parts, and yeah, well, you reset it and you're good to go. In this case, it's different. There are no safety boundaries. So basically, if I screw this up, I screw it up big time. And this pretty much goes for both of the most important axes, so X and Y. Z is kind of safe. This would be something I want to address at the same time when I'm switching over to the different mainboard, because this project could end with a bold move. You see that I'm yet again at a point where I don't really know in which direction I want to be shipping, but I know that I want to invent, research, and do something innovative. And I think this machine is like a pretty good base for it. So what we can do, we are somewhere in the large format area. We do have a very open build, which is very, very precise. This is like the most unique selling point of the whole system. If there's an application where we have to go micron level accuracy, we could do that on here. Certainly, a lot of construction sites open, especially here on this kind of flooring which I'm on and the spring situation which it's resting on, but we could figure that out. Build a complete motion system for it. I hope no one types 5 axes in the comments. I would hate to do that. Because if you have 3 axes that are micron based, don't make me do this. Don't make me even consider this. Don't even tell me that I got a 4th axis sitting there which is sub-micron based. Please don't tell me in the comments. So as you can see, there are tons of things we could do on this machine. Help me out to find something that is truly worth the effort. So with really all of that being said, my name is Jan. I build stuff so you don't have to. See you in the next episode. Bye.